Good day. The last study unit focused on chapter 15 on ANOVA, which is short for the analysis of variance. And these are just basically a set of techniques that allows us to compare multiple population means simultaneously to see if there are differences amongst them or not. So you would typically apply some treatment to a group of items or processes or people to see if they give the same results or not. For instance, let's say that a doctor has different treatments for high blood pressure, then he will assign these treatments to different groups of patients, and after an extended period of time he can compare the treatments with each other to see if the results are the same or if they differ. Or if you run different sorting algorithms through a database to sort data, you can see if the mean times differ from each other or not for these different algorithms. We'll do a hypothesis test to see if there are differences amongst the population means or not, but first we need to calculate the measures needed to do this hypothesis test. So in part 1, from section 15.1 up to 15.3 in the textbook, they explain these calculation measures to you. If you look at the outcomes in the study guide, you should be able to apply the formulas for the sum of squares, the mean sum of squares, and the degrees of freedom. And all these measures can then be summarized in a table, which we call the ANOVA table, and these values will then be used in the hypothesis test later on. If we look at the background of ANOVA, it's simply an extension of the two population t-test and z-test that we did in chapter 11, but now we are going to test 3 or more population means with each other. If we just go back to chapter 11 quickly, where we tested 2 population means, the null hypothesis and the alternative hypothesis were specified in a specific way. In the null hypothesis, we specified that the 2 population means are equal to each other, and the alternative hypothesis could be specified in any of these 3 ways. But in ANOVA, we are only interested in testing whether there's a difference between the population means or not. So we are only going to focus on this alternative hypothesis. The way in which we evaluate the differences amongst the population means in ANOVA is to compare the variance or the variation between the populations. Because if there's no variation between the population means, then they will be the same, but if there's variation between them, then they will differ. The basic procedure that we will follow is first of all to make sure that the assumptions are met for ANOVA. The assumptions are discussed in section 15.4 in the textbook, but for now it's just important to take note that they should be met. Otherwise, the conclusions that we draw from the hypothesis test might not be reliable. Then, if we check the means and they are all equal, then nothing more needs to be done. But if the means are different from each other and they are not all equal to each other, then we need to do further testing to see which means will statistically differ from each other. And these tests we call post-hoc tests, and it will be discussed in section 15.5 in the textbook. In ANOVA, we also state in the null hypothesis that all the population means are equal to each other. So let's say, for instance, that you have 4 different treatments. You apply these treatments to 4 different groups of people, and you want to test whether the results for the populations are the same. Then in your null hypothesis, you will specify that all the population means for the four different groups are equal to each other. However, in the alternative hypothesis, you are not allowed to state that all the population means differ from each other, because some of the population means might be the same and some of the population means might differ. On the next few slides, I try to illustrate that to you graphically. So in the alternative hypothesis, we would rather state that not all the population means are equal, or not all the population means are the same, or at least one of the population means is different from the rest. And you can use any of these sentences that you can remember easily. If your null hypothesis is true, then it means that the null hypothesis will not be rejected, so all your population means will be the same. So this means that there's no treatment effect that is present in your data, and that's why all your population means will be the same. However, let's say that your null hypothesis is rejected, then all the population means will not be the same, and at least one of them will then be different. So a treatment effect will be present in the data. So either all of the population means can differ from each other, so none of the treatments was the same for the different groups, or let's say one of the treatments differ from the rest, then the first two population means will be the same, for instance, but then the third one will differ from the rest. Example 15.1 is used throughout the chapter. So on page 351, they give you a bit of background on this example. So basically, they researched 20 students in a particular school district, and they wanted to apply 4 different treatments to the students. These treatments were different teaching styles, and afterwards they let the students write a test to compare the mean test scores to one another to see if there's a difference between the teaching styles or not. The 4 teaching styles that were defined is outcome-based teaching with visual aids, outcome-based teaching without visual aids, non-outcome-based teaching with visual aids, and non-outcome-based teaching without visual aids. So the 20 students were then divided into these 4 different groups, so 5 students per group. ANOVA makes use of the sum of squares to give the 3 different measures of variation that will allow us to complete a thorough investigation of the means in the hypothesis test. So the first measure that we use is SSTO, and this is the total sum of squares, which measures the overall variation within the entire data set. And then the second measure is SSTR, which is the treatment sum of squares, and this value measures the variation between the means of the different groups. And the last one is SSTE, which is the error sum of squares, which measures the variation of the individual data observations within each group. On the following slides, I will explain all of these formulas in detail, but first we need to look at the notation that is used. In ANOVA, G refers to the total number of groups or factors or treatments to be studied. So in example 15.1, our G will be equal to 4 because we had 4 different treatments, the 4 different teaching styles that was applied to the students. N refers to the number of elements within each group, and in this course we assume that all the groups are equal in size. So since we had 20 students in total in example 15.1, and we had 4 different groups, our N will be 5. Then in total refers to the total number of elements in the study. So in example 15.1, that will be the 20 students. Then Yij refers to the jth element in the ith group. So that means that all 20 students can be numbered in the different groups. I gave you an example here. Let's say that we have 4 groups in total and we have 5 elements in each group. Then it means that the first element will be Y11, since that will refer to the first element in the first group. The second element in group 1 will be numbered Y12 because that element refers to the second element in the first group, etc. Then for the second group, the first element will be numbered Y21 since it refers to the first element in the second group. The second element will be numbered Y22 because it's the second element in the second group, etc. So all 20 items or people or processes can be numbered like this. Using this notation, we can then define the following means that are used in calculating the sum of squares. The first one on page 354 is the overall mean of the entire sample. That's indicated by Y bar, and there you simply add all the elements across all the groups, and then you divide that by n total. Then you can also calculate the individual means for each group. So that will be indicated by Yi bar. So for instance, if you calculate the individual mean for group 1, it will be Y1 bar. If you calculate this for group 2, it will be Y2 bar, etc. So all you do in calculating this, you add all the elements in that specific group and you divide by the total number of elements in that group. The first measure of variation is the total sum of squares, and as I indicated previously, this measures the overall variation of the observations in the entire data set around the overall mean. So if you look at it visually, you get the difference between the individual data observations, all the dots, and the overall mean. So you will subtract the overall mean from all the data observations each time. You square that value and you do that across all the groups for all the elements. We square the different values since the positive and the negative values can cancel each other out. Then the second measure of variation is the treatment sum of squares, and this is also known as between group sum of squares, and it measures the variation of the group means around the overall mean. So visually, we look at the differences between the group means and the overall mean. For your formula, we will square the difference between the group mean and the overall mean each time. We sum it for all the differences and then we multiply it by n, which is the number of elements within a group, to take into account all the different elements across all the groups. Then the last measure of variation is the error sum of squares, and this is also known as the within group sum of squares. And like I indicated previously, it measures the variation of the individual observations within each group around the mean. So visually, it looks at the differences between the individual values within each group and the mean for that group. Also, for the second group, the individual data observations and the group mean, And then for the last group, the difference between all the individual data observations within that group and the group mean. So if you look at the formula of SSE, you will get a difference each time between the individual data observations within each group and that group's mean. You will square that value each time, and we do that across all the different groups. These three sum of square measures leads us to the mean sum of squares, which measures the mean variation. The first one is MSTR, which is the mean treatment sum of squares, and this value measures the mean variation of the group means around the overall mean. If you look at the formula for MSTR, you take your treatment sum of squares and you divide it by the treatment degrees of freedom, which is given by G minus 1. Then the second mean sum of squares is your mean error sum of squares, and it's denoted by MSE, and it measures the mean variation of the individual observations within each group around the mean. If you calculate that value, you take your error sum of squares and you divide it by the error degrees of freedom, which is given by your total number of observations minus your G, which is your number of groups. We can then use these measures to calculate our F statistic, and that we are going to use in our hypothesis test in the next section. And our F statistic is denoted by F star, and that's simply your MSTR divided by your MSE. This F statistic follows the F distribution with V1 and V2 degrees of freedom. V1 is your treatment degrees of freedom. That will give us the column in your F table, and V2 is your error degrees of freedom, which is given by N total minus G, and that will refer to the row in your F table that you will use in your hypothesis test. Okay, then all these measures can be summarized in the ANOVA table. Obviously, I can't ask you to calculate all these measures in the test or exam. So what I usually do is I take some of the values out of the ANOVA table and I ask you to calculate the missing values. So it's important for you to take note where what is placed in your ANOVA table. In your first column, you have your source or variance. In the first row, you will find your treatments, then your variance within your groups in the second row, and the third row indicates the total variance. Then in our second column, we find our degrees of freedom. In the first row, your treatment degrees of freedom will be placed there. In the second row, we find our error degrees of freedom, and in the last row, we find our total degrees of freedom, which is your total number of observations minus 1. In the third column of the ANOVA table, we find our sum of squares. So in the first row, you will place your treatment sum of squares, your second row, your error sum of squares, and your total sum of squares is placed in the last row. Then there's a shortcut that you can use in your calculations. You basically only need to calculate 2 of the sum of squares measures, and the third one you can get with this relationship, because the total sum of squares is given by the sum of the treatment sum of squares and your error sum of squares. But let's say the total sum of squares and the treatment sum of squares is the easiest to calculate for you. Then you can get the error sum of squares by subtracting the treatment sum of squares from the total sum of squares on the left hand side. Then in your fourth column, you find the mean sum of squares. In the first row, we place our treatment sum of squares, and in the second row, you will find your mean error sum of squares. And then the last value that you need to calculate is your f-statistic. The p-value will be given on your computer output, but you don't need to calculate that manually. And we will use that value in the hypothesis test later on in the next section. We can now try these manual calculations of the variation measures for example 15.1. The data is given on page 356 of your textbook. Just to recap on the scenario quickly, we had 20 students in the study, so our end total will be 20. Then we had 4 different treatments, so our number of groups will be 4, and there will be 5 observations within each group. We need to start off by calculating our overall mean. So we simply add all 20 observations and then we divide by 20 since our total number of observations is 20. So our overall mean for the study will be 69.25. Next, we calculate our individual group means. So the mean for each and every group. So for group 1, you will add all 5 elements in that group and you divide by 5 since the total number of observations in that group will be 5. So the group mean for group 1 will be 82.4, and you can repeat this then for all the other groups. So for group 2, you will add all the elements in group 2, divide by 5. For group 3, you will add all the elements in group 3 and divide by 5. And for group 4, you will add all the elements in group 4 and you divide by 5 as well. Next, we calculate the sum of squares. And we can do this in 3 columns, or you can use the shortcut relationship where you calculate the easiest 2 and then you can get the third value from there. So first, if we look at the total sum of squares in the second column, you take the difference between your individual observations and your overall mean, which we calculated as 69.25. So for each and every observation, you need to subtract the overall mean from that, you square that value, and if you sum that column, you will get your total sum of squares. The third column looks at the treatment sum of squares. So if you go back to the formula, we get the difference between the individual group mean and your overall mean first of all. So for the first 5 observations for group 1, you will use that group mean of 82.4. So you take the 82.4 minus your overall group mean, which was 69.25, and you square that value. For the second group of data, your group mean was 74.2, so you will take 74.2 minus your overall mean, you square that value. You do the same for group 3 and for group 4, and then you can sum that column. Then you multiply by n. So in our case, the number of observations per group was 5. So you will multiply the sum by 5 and you get your treatment sum of squares. Then the last column shows you the calculations for the error sum of squares. So if you look at your formula, you take the difference between your individual observations each time and your group mean. So for the first 5 values in group 1, you will take your individual value, your observation there, and you subtract the group mean of 82.4. You repeat that for all 5 values. Then for the second group, you will take your observation and you subtract the group mean for group 2 from that, which was 74.2. You square that value, you do it for all the other values in group 2. Then you repeat that calculation for group 3 and for group 4, and if you sum that column, that will give you the value of your error sum of squares. Next, we can calculate our mean sum of squares. So we already calculated the error sum of squares in the previous slide. So you simply take that value and you will divide that by your treatment degrees of freedom, which was 4 minus 1, and that will give you your mean treatment sum of squares. Then we can calculate our mean error sum of squares. We already calculated the error sum of squares on the previous slide, and you divide that by your error degrees of freedom, and that will be the total number of observations, which was 20, minus your number of groups, which was 4, and that will amount to 24.25 for your mean error sum of squares. And then the last value that you need in your ANOVA table is your F statistic, and you will simply take your mean treatment sum of squares and you divide that by your mean error sum of squares, and your F statistic will then be 27.735, and then you can summarize all these measures in your ANOVA table. In the last section of part 1, we just need to look at the computer output for ANOVA. So first of all, you have your dependent variable. That's what you observed, and it was the marks for the students, and your factor or your treatment was then the teaching style, and we had 20 observations in total. Then this next part that's highlighted in blue is your ANOVA table. So that's basically all the measures that we calculated on the previous slide for example 15.1, and it's just summarized in the ANOVA table on the computer output. Then just take note that the F value is your F statistically that you calculated manually, and the last value is your probability or your p-value that you will use in the hypothesis test in the next section. But you shouldn't be able to calculate that like I told you previously. Then if you look at your table of your group means, this is your individual group means that is highlighted over here. So the value next to group number 1 will be your Y1 bar. The value next to group number 2 will be your Y2 bar. Then you get your Y3 bar and your Y4 bar. And then the last value on the first part of the output is your overall mean of 69.25, and that will be your Y bar. Okay, then lastly, it's your turn for an exercise. You can do exercise 1, please, to calculate all the measures for this data, and you can summarize the values in an ANOVA table then. I did provide the output on the next slide for you so that you can compare your answers to the output, and all the calculations was then also uploaded on to eFundi, so you can check your answers there as well. Thank you.